1, and then we go on to type 2. So would you like to make up one? Would you like to make up a rational function of type 1? Same degree of a same degree. I have one. Let's say x minus 1 times x plus 2 divided by x squared. I'm going to put a 2 in front. Divided by x squared minus 4. I claim it's type 1, meaning same degree over same degree. So what is the degree at the top?
2.
Excellent. What is the degree of the denominator? Excellent. Is it type 1? Yes, it's type 1. Very good. Awesome. We continue by simplifying it. 2x minus 1, x plus 2, over x plus 2, and x minus 2. We have to continue with the domain, as we know. What is the domain of this function? Can anyone help? The domain of this function. I have 2 more friends that I think I have to move around very soon. Yes. Okay. Okay, I'll move her then this time. Okay, so careful. Negative infinity to negative 2. Negative 2 to 2. Awesome. Excellent. So obviously x cannot be plus or minus 2. However, this is what happens now. Please remind me if I should say, I'm asking you to refresh your memory and maybe you paid attention last time. And what did I say about x equals negative 2, right?
Is there a hole?
Excellent. X equals negative 2, hole in the graph. Since the final simplified form is 2x minus 1 over x minus 2, what will x equals 2 represent? Excellent. Well done. Good. So now let's talk about the end behavior. Last time I did not write this. I remember clearly I did not. So now I'm going to write it. For type 1 rational function, horizontal asymptote is leading coefficient over leading coefficient. I didn't want you to just memorize this. I showed you an example by factoring out the degree, top and bottom. But this is what it is. So this is y equals. What is the leading coefficient of the top?
0.
What is the leading coefficient of the bottom? So the horizontal asymptote will be 2. So then y equals 2 horizontal asymptote. Well done. So the final simplified form of this function is correct. 2 over 1.
You put 0.
Oh. Sorry. My apologies. Okay, so then it's 2x minus 1 divided by x minus 2. We have to plug in negative 2 in this function now. Once we removed the factor that created 0 over 0, in this case, now we have to put in this value in the function, find f of negative 2, because these two numbers will not be infinities. These will be infinities. How do I know? Because x equals 2 is a vertical asymptote. What I don't know is the sign. I'll come back to the sign in a minute with 1.9 and 2.1. So when we plug in negative 2, we get 2 negative 2 minus 1 divided by negative 4. And the answer will be negative 6 divided by negative 4, or 3/2. Do you agree with 3/2?
Yes.
Thank you. So then we have 3/2 on the left and 3/2 on the right. Okay, so now we plug in 1.9. I only need the sign. When we plug in 1.9 here, the top is positive, but the denominator is negative. So what is the sign of this infinity? Perfect. with 2.1. 2.1 plus 1, 2.1 minus 2. The sign will be? Awesome. Can this function be symmetric if it has a vertical asymptote at -2 and it does not have one? I'm sorry, it has a hole at -2 and a vertical asymptote at 2, and it does not have, it's not symmetric on both sides. Can it be symmetric? It cannot be, but I still have to write that f of negative x will not be negative f of x, and it will not equal f of x. Not symmetric. Because remember, this is part of the list of items that I have to present before I graph. Okay, so now I'm looking at my table. I have not graphed the function, we just made it up. So here is my take on it. I know I look silly, but I'm hoping that it will help you understand this. From approaching 2, it goes through a hole at -2, 3/2, which is 1.5. I forgot about 0, so let's plug in 0. I need the x-intercept. I can continue without the x-intercept. So 0 minus 1, 0 minus 2. So -2 divided by -2, this is 1. Okay, so from approaching 2, it will go through a hole at -2, 1.5. You will cross the x-axis at the y-axis and then the x-axis. We forgot one more thing. I forgot one more thing. So the x-intercept when x is 1. Okay, one more time. From approaching 2, going through the hole at -2, 1.5, crossing the y-axis at 0, 1, crossing the x-axis at 1, 0, and going towards -infinity. So from approaching 2 to -infinity. On the other side, from positive infinity, approaching 2. No problem, I hope. So let's graph it. We don't need anything except the table. Everything else is redundant right now. The table tells us what to graph. When we graph functions with asymptotes, we must graph the asymptotes first. That's the first requirement. So at 2, x equals 2, and at y equals 2. Now we plot the points. -2, 1.5 is this hole. 0, 1 is this point. 1, 0 is this point as we expected. And here's the graph. We knew everything about it. On the other side, it's quite easy. No problem. So this is f of x. 2, x minus 1, x plus 2 over x squared minus 4. You can check with the graphing calculator. Be very careful because the graphing calculator will not give you this point. It would be very difficult to see it. I'm sorry?
Why? Why is it
The calculator is not as smart as you are. Here it is. So when we graph 2 parentheses and parentheses again, be very careful with parentheses here. X minus 1, close. Open another one with x plus 2. Close, and divide by, in parentheses, x squared minus 4. I don't need the second parenthesis here. And I need to put the second function, which is y equals 2, otherwise the calculator will not graph it. I will use zoom 6. Here it is.
It's not.
So let me show you one more time. I'm so sorry. So let me show you how I put the function in, because I was hoping that you would see that. So 2, I put 2 sets of parentheses around the numerator. Yes, Caleb, any questions? What is it?
How do you find the most class?
How did I find what?
The vertical asymptote.
Oh, okay, very good. Okay, so double parentheses around the numerator, of course, and then the denominator x squared minus 4. And I have to put in a function. The calculator doesn't know to put in by itself. Yes, any questions? Any questions, Ryan? Any questions?
I was thinking out loud, my bad.
So when we graph, we will see this is the graph as we expected, but it does not show what's happening here. You can't see unless you do zoom in or change the viewing window into, let's say, -2. No, that's exactly where it is. -3 to -1, and y minimum, -1, y maximum, let's say 3. I hope we can see it. Yes, we see it, but it's very, very difficult. That's why do not rely on the calculator or copy anything from the calculator, because it doesn't mean anything. Everyone can copy from the calculator, right? Okay. Now, I think we're ready to move on to type 2. So here's an example of type 2. Ready? Ready for type 2? Okay, so let's say f of x equals x divided by x minus 1 times x plus 2. I claim that this is type 2. Is it? Because the degree at the top is
Plus 1.
exactly. That's good enough. Awesome. Great. So the only difference from the previous one is the horizontal asymptote. What do you think the horizontal asymptote would be? Don't say anything before I give you a hint. When x approaches infinity, huge, this is much smaller than this. So it's like 1 divided by infinity. So what would be the horizontal asymptote for all type 2 forever?
1.
0.
Very good. 0. That's the only difference. There is nothing else. So whatever you give me as domain, I will immediately write this, and it's done. That's the end behavior. Because it's type 2. And the numerator is much smaller than the denominator at infinity. Yes?
These are for all type 2.
All type 2 have horizontal asymptote 0. Type 1, leading coefficient over leading coefficient. Type 2, always 0. Perfect. So now I'm waiting for the domain. Perfect. Since x equals -2 and x equals 1, x equals x minus 1 and x plus 2 do not disappear, what do we conclude immediately? They are both vertical asymptotes. Excellent. Good. So when x is 0, y is 0. We know infinity is left and right, but we do not know their sign. We're done. We just have to plug in -2.1, -1.9, 0.9, and 1.1. Don't calculate anything. We only need the sign. So for these two, the top is negative. Now, negative and negative. Negative, negative, negative. What sign do we have on the left-hand side of the first vertical asymptote? Awesome. Now with -1.9, this is negative, but this is positive. Excellent. With 0.9, this is positive, this is negative, this is positive. Excellent. With 1.1, positive, positive, positive. That's all. Not symmetric. It cannot be symmetric if it has a vertical asymptote at -2 and at 1. I don't want you to spend too much time on these functions. They are very important, but you should have no difficulties with them. First, we graph the vertical asymptotes, or all asymptotes. Now you understand that this is an overkill. There is no need, because it's already there. It's the horizontal asymptote, it's the x-axis. Okay, so let's see what we have. Let's look at the table. The table tells us everything about the function. Ready? It starts at 0. and drops to negative infinity on the left-hand side of the first vertical asymptote. Then it comes from positive infinity, it crosses at the origin, and it goes to negative infinity on the left-hand side of the second asymptote. And then from positive infinity to 0. One more time, from 0 to negative infinity, from positive infinity to negative infinity, from positive infinity to 0. That's it. So 0 to negative infinity, positive infinity crossing at 0, going to negative infinity, positive infinity going to 0. And that's type 2. You can find as many points as you want. The shape will not change. It will still be the same. Any questions? Say it again.
Where did you find the point
When x is 0, y is 0. 0, 0, 0, 0 over negative 2 is 0. Better? It's the x and the y-intercept, the origin. Any questions?
So on the test, if this comes on the test, we just draw the vertical, horizontal, so just draw the general shape.
Yes, I'm not expecting you, if that's the question, I'm not expecting you to find 10 points. If you want to find 10 points, you can. There is no need. There really isn't a need. But if you want to be more exact, you can find as many points as you want. I'm fine with that. Okay, any questions on what we looked at?
Type 1 and type 2.
Yes, there's also type 3, but they crossed it out. Last thing before we start chapter 6, I wanted to go over this. Solving polynomial and rational inequalities. Ryan, yes, any question? Okay, so let's choose from here. Any rational, we've looked at least 3 or 4 problems like this, so let's pick something else. We have not looked at rational ones. That I know for sure because we just talked about rational functions. So these we have not talked about. But here we chose 1 or 2. So which one? Any preference?
Easier one first, harder one next.
Okay, so if you want to do easy one, I will do C first. And then I will choose either H or I. Yes? Okay, perfect. So let's look at E from the handout. So rational inequalities. Perfect. So we have 5 minus x over x plus 2 greater, oh no, actually it was less than 0. 5 minus x over x plus 2 less than 0. Good. We have on the left-hand side a ratio, and we have on the right-hand side 0. This is typical for the studying the sign of the rational function using the table that I showed you a long time ago. So x is the variable in the problem. It can be anything. Then instead of writing this, I'm going to write negative x plus 5 in descending order. And then I'm going to write the next factor, which is the denominator. And then finally the ratio. Exactly what we covered, we did before. Then I'm going to ask you, where is the first one 0? And you'll say for x equals, perfect. Where is the second one 0? Excellent. In ascending order, great job. In ascending order, we have negative 2 and 5. Then we know there is a 0 somewhere under a particular number for negative x plus 5. Under? It's a silly question, of course. Under? It cannot be. Good. Very good. So now what happens to the ratio when x is negative 2? Very good, undefined, awesome, great job. And what happens to the ratio when the numerator is, when the x is 5? Very good, awesome. 0 divided by a number is 0, perfect. So now can anyone give us the sequence of signs? Now we know polynomial function of higher degree. This is a negative leading coefficient. Does it look like this or like this? Yes, so it's from positive to negative. Very good. So the sign of the first one is from positive to negative. What about the second one? Indeed. Because the leading coefficient is positive. Awesome. That's why I arranged both in descending order so we can identify the leading coefficient. Well done. So now on the first subinterval, we divide the positive by a negative. What do we get? Great job. Second subinterval. And the last one? Only now I ask myself, what do I pick? Which sign is less than 0? Negative. So the ratio is negative here and here, so I have to choose this. And that will be the final solution. Ready to write it? How do we write the final solution? Notice that this is strict inequality, no equal symbol. So negative infinity, negative 2, so x in the interval, union. Very good. With parentheses in both cases. Very good. Well done. Thank you. Again, if you read this and you find that this method is easier for you, please use it. Everyone is different, and it's fine by me if you use a different method, always. Questions? Questions? Yes, go ahead. Flynn, what was the problem?
I'm just so confused as to what we did this time before.
We are solving inequalities that are rational. Rational inequalities. And this is from the handout. Polynomial and rational inequalities. Is that better? Okay, perfect. Everyone? Yes? Other questions? Could you follow so far? Okay.
So,
Yes?
Finding what's less than 0, you're finding where everything on the domain is big.
No. So, the question here is, find x such that that expression is negative. That whole thing, 5 minus x over x plus 2. Maybe
Right, it's
is that,
negative on that entire domain,
it's not the domain.
or not the domain, it's just the interval,
We're not talking about the domain here.
right? Just
The
talking
domain would be everything but negative 2. That has nothing to do with this question. In this question, we are asked to find what x should be for the inequality to be a true statement. The inequality is a true statement only if you pick here or there and plug it in. If you pick between negative 2 and 5, it will be greater than 0. Right? No, it's okay. It's okay. Maybe I didn't have, maybe it's fine. I should have just put it in those words. If you don't ask, I don't know what to correct. So that's why I'm relying on you to ask. Is this better? Yes? Yes? Okay, we will have another. Let's look at another. We selected H. H or I, doesn't matter. Okay, perfect. So this is 6 divided by x squared minus x greater than or equal to 1. Perfect. Remember, the table does not work if we do not have a ratio on or a product on one side and 0 on the other. This is not the case here. This inequality needs work before it's ready for the chart. So what do you think I'm going to do next? Of course, of course. What do you think I'm going to do next? I have 0 now, but I don't have a ratio or a product here. So what will I have to do next? The least common denominator. Great job, of course. Which is? Very good. So then this one needs an x squared minus x. So I have x minus x squared and plus x. Everyone okay so far? Nothing new, right? We've done this before. Okay, perfect. I will arrange the numerator in descending order. I will factor completely the denominator. How? I will factor the -1 in the numerator, x squared minus x minus 6 over x minus 1. What do you think I'm going to do next?
Identify your zeros.
Factor.
Yes, I will factor the numerator, but right before I do factor the numerator. What do you think? Yes?
State restriction.
I will, but we will have to put them in the table anyway. But you're right. Yes, x cannot be 0 and 1. Yes. Something else bothers me. What do you think bothers me? Yes, of course, this bothers me, like always, right? So x minus 3, x plus 2 over x minus 1 less than or equal to 0. I don't care for that minus in front. It will mess me up. Multiply both sides by -1. Get rid of it. And now I have how many factors I need to present in the table, because now this is table ready. How many factors?
4.
Yes, 1, 2, 3, 4. X is the variable in the problem. X minus 3 is the first factor. X plus 2 is the next factor. X is the next factor. X minus 1 is the next factor. And of course, the whole thing. X minus 3, x plus 2, x minus 1. How many zeros will you give me? Of course, you'll give me 4. I'm ready in ascending order if possible.
3.
-2 first.
-2, done.
0.
0, done.
1.
Done.
3.
Excellent. Done. Perfect. So now where is the 0 in the first row? The 0 in the first row is under?
3.
Excellent. The 0 in the second row?
3.
Excellent. Next row.
0.
And the last one. Now what happens under -2, under 0, under 1, and under 3 to the entire ratio? No, not at all. So under -2, what do I write? Good. Under 0, what do I write? Excellent. Under 1. Excellent. Under 3. Excellent. Great job. There is no need to think, right? All these linear functions have a positive leading coefficient or positive slope. Four negatives.
Positive.
Excellent. 3 negatives.
Negative.
2 negatives.
Positive.
1 negative. And no negatives. Good. Only now I choose which sign is less than or equal to 0. And what will you choose? You will, yes, very good. So x in the interval. -2, 0, we have to discuss what's happening there. And 1, 3. But please be careful and tell me what is at -2. Excellent. What is at 0? Right. Excellent, because it's undefined. What is at 1? And what is at 3?
Bracket.
Excellent. It looks like a little puzzle. I think you're seeing what's happening here. Yes? You feel better? Do you feel better about this table? Really is nothing to it. Okay, good. Anything else you would like to go back to polynomial and rational functions? Is there anything else we want to go back to? Which one? What? did he say? Okay, so I would like to start exponential functions. So we have two more functions to look at before we start trig. And we need a lot of time for trig. So that's why I'm trying to move forward. Any questions? Okay, so how many functions we looked at? Radical, polynomial, absolute value, rational, radical, right? Radical, cube root, and the square root. What else? So we have two more to look at. And they are exponential and log. So let's start with exponential. That's chapter 6. Why do you think these two functions are together in the same chapter? Exponential and log. They are inverses of each. Exactly. Right. Very good. Well done. Okay, so let's start with the exponential. 6.1. Exponential. Why do you think this function is called exponential? Because the variable is the exponent. This is the variable, which is the power or exponent. This is the base, which is a number, but it has restrictions. So let's discuss what's happening here. Can I raise -2 to the 4th power? Yes, I get 16. Can I raise 0 to the 3rd power? Yes, I get 0. Can I raise 1 to the 5th power? Yes, I get 1. However, these situations are not allowed in the exponential function. The base of the exponential function can be greater than 1, strictly greater than 1, or between 0 and 1. The question is, why? Why can't I have the base of 1, 0, or a negative number? So all these are possible, but not for the exponential function. And the reason is, if we allow 1, negative number, and 0, the inverse function will not exist. This is the only explanation. The inverse function will not exist. So for that reason, we have to remember that the exponential function cannot have 1, 0, or a negative number as its base. Okay, so let's look at two shapes. Here will be one example, like 2 to the x, for the first situation in which the base is greater than 1. And let's look at f of x later on as 1/2 to the x, where the base is between 0 and 1. Yes, there will be two different shapes, and they will have different properties. So two different functions, two different shapes. Pretty similar with a linear function having a positive slope and a negative slope. Two different shapes. Same thing here. Same idea. Okay, so let's first identify the domain of an exponential function. Notice when I'm talking about the domain, I'm talking about x. When we talk about the base, it's a different story. We're not talking about the base now. We're talking about the domain of this function. So what do you think? So let me give you a few hints. 2 to negative 1, 1/2. 2 to negative 2, 1/4. 2 to 0, 1. 2 to 1, 2. 2 to 2, 4. So what do you think the domain of this function is? One more time. -2. 1/4. Exactly. It's a friendly function. Very friendly. No restrictions. This function does not give us any headache. None whatsoever. It's defined everywhere. It's a friendly function. So let's say I'm going to pick -2, -1, 0, 1, and 2. Do we need that many? No. But let's identify the y coordinates. So please plug in -2 and give me the answer, and then plug in -1 and give me the answer, and then 0, 1, and 2. With -2, what do I write? Awesome. With -1, very good. With 0, perfect. Not 0. 0 raised to 0 is not 1, and anything other than 0 raised to 0 is 1. So 2 to 1. 2 and then 4. Now, we have not done this before, right? We analyze the end behavior for polynomial functions in one way and for rational function in a different way. But this time, we don't have a real tool. So let's discuss slowly where the function is going. 1/4, 1/2, 1, 2, 8, 16, 32, 64, 128, 10,000, 15,000, 10 million. Where am I going?
To infinity.
Excellent. Good. Now let's try this way. 1/4, 1/8, 1/. It's 1 over. How do I get the negative? It's 1 over. Nothing is negative here, right? So it's gonna be negative. One more time. 1/4, 1/8, 1/16, 1/32, 1/64, 1/128, 1/1,000,000. Indeed. So we have not seen this before. Y = 0 is a horizontal asymptote at -infinity only. So this function basically looks like this. A horizontal asymptote on this side and blowing up on the other. So let's graph it. So -2, 1/4, -1, 1/2, 0, 1, 1, 2, etc. And this is the graph of 2 to the x. It has the highest growth possible from any function we've studied so far. Highest growth possible. What can we say about this function? A lot. I can say that it's defined everywhere. I can say that its range is
0 to infinity.
excellent. I can say that it has a y-intercept but not an x-intercept. What is the y-intercept?
0.
Perfect. I can say that it's increasing on all its domain. I can say it's 1 to 1. I can say it has an inverse function. And by the way, can you please give me a couple of points so I can graph the inverse function? What is this line? Excellent. Great job. Thank you for remembering that. So please give me a couple of points so I can graph the inverse. We don't even know what the inverse is yet, but we can graph it. We cannot just make up points, right? We have to look at what we have here. We're talking about the inverse function. We have to reverse the points so I can plot, right? We know that. We cannot just pick -5, 3. So we have to look at what we have. 1/4 -2. I completely agree with 1/4 -2. Great job. 1/2 -1. Excellent.
1, 0.
Excellent. Yes, Flynn?
Yes.
You had a question?
No, I
Oh, I'm sorry. I'm sorry. Arthur, you had a question? No. Okay, I'm sorry. Next. 2-1 indeed.
14.
Very good. Awesome. Plenty. That's good enough. My graph is not perfect, but this is the inverse function for sure of 2 to the x. Although my graph does not show that perfectly, it is the inverse function. We plotted, we reversed the ordered pairs. Of course, that will be the situation. So one more time, let's write here. Domain of the exponential is a -infinity to infinity. And the range, you gave it to me 0 to infinity. Now, the inverse function of the exponential will have domain and what range? Very good. Awesome. Thank you. And the range? Right. So, although the exponential function is a friendly function, what can you say about its inverse?
Inverse.
Its inverse is not friendly. Its inverse is not a friendly function because it's not defined everywhere. This is how I call friendly. I call this friendly. It doesn't give us any worries, nothing. We don't have to worry about anything, but here we do when we get to it. Let's look at the other shape. Here we have 1/2 everything to the x power. What is the domain of this function, do you think? Indeed. It's an exponential. No matter what exponential, it will always be defined everywhere. Good. Let's pick the same points, -2, -1, 0, 1, and 2. And please present the calculations. Tell me what you determine, what you get. Because then I would like to look at some applications of exponential. So after we graph this one. Ready? When we plug in -2, what do we get? Excellent. When we plug in -1, we get? Excellent. When we plug in 0? Excellent. 1 and 2?
1/4.
Excellent. Now we have to figure out the end behavior, please, slowly. 4 to 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128. Excellent. Now the other way. 1, 2, 4, 8, 16, 32, 64. Excellent. Which means y equals 0 horizontal asymptote at infinity only, not at both sides, as we know from rationals. Okay, perfect. Let's graph it. -2, 4, -1, 2, 0, 1, 1, 1/2, etc., etc., etc. So this is 1/2 to the x. The reason I did not present a horizontal asymptote is because it was already there. So always remember, when we graph functions with asymptotes, the first thing we do, we graph the asymptotes. The first thing we graph. Perfect. So what can you say about this function? A lot. I can say that the domain is all real numbers. I can say that the range is 0 to infinity. I can say that this one is decreasing on all its domain. I can say that it's 1 to 1. I can say that it has an inverse function. I know nothing about the inverse function just now, but I can graph it. So this is y equals x. Please help me graph the inverse function. 4, -2. Excellent. Great job. 2, -1. Oh, this was not 4. Sorry. 1, 2, 3, 4. Right here. So 2, -1. Excellent. Where the function crosses y equals x, so will the inverse. Because if you reverse that point, it's going to be the same. 3, 3, 2, 2, 2, 2, 2, 4, 4. Right? So that's more than enough. This is the inverse function of 1/2 to the x. Notice that both functions are decreasing. If the original function is decreasing, so is the inverse. If the original function is increasing, so is the inverse. Okay, so I would like us to look at a first application about compound interest formula. So the formula will be given to you. So here it is, compounded interest. Let's write it because I need to explain what each item represents. So A equals P, 1 plus R over N raised to NT. Let's assume we deposit money. So then P is the principal. If we borrow money, P is still the principal. A is the accumulated value. What does it mean? If I borrow $10,000 today and I need to pay it back in 5 years, I will have to pay much more than I borrowed. That will be the accumulated value. If we deposit $10,000 today, and if we want to keep it for 10 years, let's say, in the bank, then we will get the entire amount of the accumulated value. Okay, R, lowercase r, annual interest rate. Lowercase t, time, in years. And lowercase n, the number of times the interest is compounded per year. Recalculated. Number of times interest is compounded per year. I would like to look at, let's start with 31, and then I'll let you choose any problem you want. An account is opened with an initial deposit of $6,500. So this is problem 31 on page 477. Yes, any questions? Any questions? Okay, so 6,500, what does this mean? What does it represent? Very good, awesome. Then it says, and earns 3.6% interest compounded semi-annually. So first of all, what is 3.6%? Very good, which we cannot use in that form. It has to be changed into a decimal number. Compounded semi-annually. What does that mean? How many times will they compound the interest per year?
Okay.
Very good. So what is that?
That is
N. Very good. Awesome. I didn't hear it. I'm sorry. What will the amount be worth in 20 years? So what is 20 years? Very good. So we're basically asked to find the accumulated amount. So if we keep it for 20 years, we want to find the accumulated amount. So then A equals P, 6,500, 1 plus 0.036 divided by 2, raised to N times T, which is 40. We can do this by hand. So let's put in the graphing calculator. So 6,500, parentheses, 1 plus 0.036 divided by 2. You can divide that if I just was lazy all of a sudden. Okay. And in 20 years, we will get, if the interest is compounded semi-annually, 13,268.58. That is the accumulated amount in 20 years. Questions?
So like that's how much money he's gonna have after the.
Yes. So if we deposit $6,500 today, and the interest, yes, and the interest is 3.6% per year, annual interest rate, and they compound interest twice a year, recalculate it twice a year. At the end of 20 years, we would have 13,263. Yes. Any questions? Okay. Okay, moving on. Real world applications. Ready? So in the year 1985, a house was valued at 110,000. By the year 2005, the value had appreciated to 145,000. What was the annual growth rate between 1985 and 2005? Assume that the value continued to grow by the same percentage. What was the value of the house in the year 2010? Okay, it's a mouthful, right? Let me, 1 second, let me stop this.